video is going to cover graphing quadratic functions. And we've graphed a lot of functions over the course of the year, but the truth is most of them have been linear functions or lines. A quadratic function, if we think about things that are not linear, most of the time we're going to see something like this. We call this either a parabola or a quadratic function. And so when we see a curved line like this, most of the time we're dealing with some type of parabola or a quadratic function. And that's what this video is going to go into a lot of detail on. So when we're looking about quadratic functions, there's a couple really important terms that we have to know. The first term is the vertex. And so when we're looking at the vertex, we are looking at the maximum or the minimum point. So these terms here are definitely connected. Now what's important is that a quadratic function is always written in the form something times x squared plus something times x plus a third term or a constant is equal to y. There's usually something times x plus something x squared plus something times x again plus something equals y. And we usually refer to these terms as ax squared plus bx plus c. And the thing that's important is that this a value tells us if we are opening up or opening down. So this one right here is what we call opening up, which means that the a value is positive. Any positive number makes the quadratic open up. Where this problem here, where we're opening down, our vertex, in this case, is the maximum point. That means that the a value here is negative, and we are looking at the maximum for our vertex. Now, the axis of symmetry, here's the thing about quadratics that make them a little bit easier to graph than lines are sometimes, is we have the graph is split in half through the vertex. So here is our axis of symmetry, which means that across the axis, or things that are equal distance away from the vertex, should be equal points. And if we notice when we look at this top equation, we are looking at equal points, equal distance away from the axis of symmetry. For this problem here down at the bottom, it's going to be the same case. If we look at these 2 points here, they're equal. If we look at these points here down at the bottom, they're also equal because they're equal distances away from the axis of symmetry. Now, if we covered domain and range a little bit before, but the way that we remember the difference between domain and range is domain comes first in the alphabet. So this covers our x values, and our range covers our y values. And we really care about what they can't be. So in this problem up here, my domain would be every real number of x's possible, because this is going to infinitely continue this direction and infinitely continue in the right. Whereas the range would be nothing below this point. As remember, domain comes first in the alphabet, so x's and then y. So let's look at the graph of a quadratic function. So here's an example of a quadratic function. If we remember, the form is ax squared plus bx plus c. So the first thing I like to do is I like to identify what my a value, what my b value, and what my c value are to help me solve this problem. So my a value is the number in front of x, which is invisible, but if we remember, Ann's method tells us this number should be a 1. Our b value is the number in front of this x here, which should be a 4. And our c value is the constant left alone, or 6. In order to graph this using a table, we need to know where the vertex is. And if we remember that picture, our vertex is either our minimum or our maximum, depending on if our a value is positive or negative. This a value is positive, so that this means we are looking for the minimum because our parabola is going to open up. And here's probably the most important part of a quadratic function, is in order to find the vertex, we are looking for the x value that is equal to the opposite b over 2a. So for this quadratic function, our vertex would be -4, because that is the opposite of b, over 2 times a, and our a is 1. So we have -4 over 2, or -2. And this equals the x value of our vertex. So that means our vertex is along here, which means that this is our axis of symmetry. So somewhere along here is our x value, and that's going to be important as we learn how to graph a quadratic function. So we know that the vertex has an x value that is equal to -2. And we are going to graph by going back to our tables that we covered a bunch in the last few units. We're looking at x and y as normal. And here is the most important thing about quadratics. Once I have found what the x value for the vertex is, because everything must be equidistant away from the axis of symmetry, that means that my x value as -2 is going to be here in the middle of my table. And we're going to do that because the value that's 1 above and 1 below will have to match. The value that is 2 above and 2 below will have to match as well. So I got to pick a number that is 1 below -2, which is -3. 2 below would be -4. That would give us -1 and 0. And from here, I'm going to plug these into the equation to help me graph. So I always want to start with the vertex, because that is the middle of my equation. So I do -2 squared plus 4 times -2 plus 6. This is 4 plus -8 plus 6, which means my y value is equal to 2. Which means if I did this correctly, this should open up this direction. Now, the way that I can check this is I do my -3 and my -1 inputs, and they should match. And if they do match, that means that I have done my vertex correctly. If they don't match, it means I've made a mistake. This is +9 minus 12 plus 6, which is +3. The bottom equation here, I plug in -1 into my function. I get 1 minus 4 plus 6, which is also 3, which means that my vertex is correct, because straight through my axis of symmetry is lining up on both sides. Now, for these last two parts, I actually only have to pick one of them, because I know that it should match. If you ever have the opportunity to pick a 0, you're in great shape. 0 plus 0 plus 6. And by definition, this must also be 6, because these two numbers are equidistant from our vertex. That's 4, 5, 6, and 6 over here. And I could keep that process up, going infinitely in either direction, but for the sake of time, I am not. And now I'm going to try to graph this line, but it's Mr. Schmidt drawing it, so it's entirely possible this makes a mess. Ugh, that's not my greatest. But there we have graphed a quadratic function. Our domain, because it can cover any x values, is all real numbers. And our y values, or our range, is anything that is greater than 2. And there's a lot of ways to write that. You can say all real numbers bigger than 2. Or you can write this as 2 to infinity. That's sometimes how you'll see it written. Or you could say all real numbers greater than 2. Now, we only did one example here, so a lot of people will watch the retake video by choice. But as always, if you have any questions, please let me know.